Okay, let's get started, please. So last time we were talking about some observations regarding eigenvalues and eigenspaces, and what we finished with, but hadn't really started, was the product and sum of a matrice's eigenvalues. So we said that in fact there was something cool that happened if you had a matrix and lambda 1 through lambda n, the roots of the characteristic polynomial. So let's let p lambda denote the characteristic polynomial. The roots of p, possibly with repetition. Okay. If you looked at all the roots of the characteristic polynomial, then something interesting happened, which was one, the product of the roots turned out to be excuse me, the determinant of the matrix. Okay. This notation is product, right? A big P, just like the big S means sum, right? And the sum of the roots turns out to be the trace. Like last time, we looked at this matrix, and we found that it had eigenvalues 2, and 3, right? And you see that, right? If we look at the product, we get 6. Well, 6 is the determinant of this, right? -6 minus 12. That's 6, right? 2 times 3 does equal the determinant of the matrix, and 2 plus 3 does equal the trace of this matrix, right? 6 minus 1 is 5, just as 2 plus 3 is. Okay. So that example that we worked on last time, seems to support our theorem, and that's not surprising. Okay. So the proof of this is a little bit intricate, but let's start off with just an exercise. Here's the exercise: x minus 3, x minus 2, x minus 5 equals 1. Okay. This is not really an exercise, but so if you're looking at this thing, say, okay, well, you can multiply it out, or you could just start counting. How many x cubes do I have? I have 1 x cubed. Right, there's only one way to get x cubed. Right. How many x squareds do I have? How many x squareds do I have? Well, I could have minus 3 times x times x. I could have minus 2 times this x times this x. Or I could have minus 5 times this x times this x. Right? So I have minus 10 x squareds. Right. How many x's do I have? Right. How many x's can you get out of this? Well, you could have x times -2 times -5, so that would give me 10 x's. Right. I could have this x times -3 and -5. That's 15 more x's. We have this x, right, 6 of them. Right. And then how many ones do I have? Well, there's only one way to get the ones, and that's by taking this. This times this times this, that gives me -30. Right, so that gives me x cubed minus 10x squared plus 31x minus 30. Right. So just right? Just a maybe simpler way. If somebody gives you a bunch of things, then it says, well, what's the factor, what's the coefficient of x squared? Well, it's easy to figure out. I mean, it's not so easy, but you can do it in this way. Does everybody see what I'm doing? Okay. So instead of multiplying it out, you can count. Okay. And that'll be basically what we're doing in the proof of this theorem. Okay. So we're going to give the idea of the proof in the case of a 3×3 matrix. And for an n by n, the proof is basically the same. So actually, let me use the whole board. It's going to be kind of long. So first notice that the characteristic polynomial we know is the determinant of a minus lambda I, right, is a polynomial of degree 3. Right? It's a polynomial of degree 3, and since it is a polynomial of degree 3, it has 3 roots. Some possibly repeated. And let's call those roots lambda 1, lambda 2, and lambda 3. Okay, so that tells us we can express the polynomial as some constant times lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. Nothing? We haven't done anything? Okay, now let's notate P of lambda also as B0 plus B1 lambda plus B2 lambda squared plus B3 lambda cubed. Okay, let's give names to the coefficients of each of the powers of lambda. Let me call this fact star sub 1. Okay, and if we think about it for a second, we see that notice that B3 is the same thing as C. Right? The coefficient of lambda cubed is C. Right? This C. And the coefficient of lambda squared is going to be C times negative lambda I from I equals 1 to 3. Everyone okay? This is the only one that requires a bit of thought, right? And it just follows from that exercise that we did before, right? What's the coefficient of lambda squared if we look at this thing, right? Well, you could take C times lambda 1 times lambda times lambda. You could have C times negative lambda 2, lambda to lambda. You could have C times negative lambda 3, lambda lambda, right? So you're going to get C times the sum of the negative lambdas times lambda squared. Right? So the coefficient of lambda squared is going to be this thing. Okay. So okay. So however, we know P of lambda is the determinant of A minus lambda I. that's to say the determinant of a11 minus lambda, a12, a13, a21, a22 minus lambda, a23, a31, a32, a33 minus lambda. Right? Which is a11 minus lambda times the minor determinant of the minor minus a21 a21 times the determinant of a1 a12 a13 a31 a33 minus lambda plus a31 times the determinant of a12, a13, a22 minus lambda, a23. Right, so we're just taking the expansion by minors down the first column. Okay, so we're going to relate everything back together. So observe, the only term involving more than one diagonal element of a minus lambda I is a11 minus lambda, a1, a22 minus lambda, a33 minus lambda. The only term in this polynomial, right? When you multiply all these things out, right? When you multiply all these things out, the only term that involves more than one, more than one of the diagonal terms is this one, right? Where you take this times this. Right? When you multiply this out, you get this times this minus this times this. You get this times this minus this times this times this minus this times this. Right? All of these terms involve only one of the diagonal elements, right? Except for this one, a11 minus lambda times this thing here. Right? So when you work out work out what this is, right? That's the only term that has more than one diagonal element. Right? So what does that tell you? That tells you that what's B3? Right? The coefficient of lambda cubed, namely B3, is negative 1 cubed. Right. Yes, Mia?
Why?
So, coefficient of lambda cubed, right? We're looking, the coefficient of lambda cubed in the characteristic polynomial, right? Mm-hmm. This is the only thing in the characteristic polynomial that has a power of lambda greater than 1 in it, right? go back here. This thing here is the characteristic polynomial, right? This is the characteristic polynomial, right? What is it? It's going to be a11 minus lambda times a22 minus lambda, a33 minus lambda, a11 minus lambda minus a23, a32, minus a21, a12, a33 minus lambda, plus a21, a13, a31, etc., etc. Right? And you see that the only thing that has more than one of these diagonal elements in it is this first one. Okay. So what does that tell you? What's going to be in P3? I'm sorry, in P lambda. What's the coefficient of lambda cubed? Well, there's only one way to get lambda cubed here. It's this, right? It's -1, -1, -1, so we get -1 cubed.
I just don't get why is it -1? Because we can choose. Why is it -1?
If I said, like, here I have a polynomial, 5 minus x, 6 minus x, 2 minus x, and I said, what's the coefficient of x cubed? What's the coefficient of x cubed, right? You can say, okay, well, the only way I can get x cubed is to take this -x, -x, and -x, right? So that's going to give me, -1 cubed x's.
Oh, okay. I get it.
Yeah. Yeah. So that's all we're saying here.
Okay.
Yeah. So yeah. So the coefficient is -1 cubed, and the coefficient of lambda squared. Well, what's going to be the coefficient of lambda squared? Well, we're going to get a11 negative lambda, a22 negative lambda, a33 negative lambda, right? So we get that b2 is going to be a -1 squared summation a I from I equals 1 to 3. And I'm putting these -1 cubed and -1 squared because when you have n, then it's, you have these things to an nth power. So I know you know that this is just 1. Okay. Okay. Everybody on board? Anybody have questions? Any questions up until this point? So we have all our facts, and now we're going to put them all together. So, okay. So, okay. So all together, our first observation is that P lambda we can think of as some constant, right? The constant is B3. B3 is -1 cubed. -1 cubed times lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. Okay. And that's from fact star 1. Right. Star 1 says, was expressing P in terms of its roots with some coefficient on the beginning, and here we see that coefficient. Here we see that the coefficient is -1. Okay. Fact number 2. Oh, let me stop for a second. So. P at time 0. If we evaluate P at 0, you see what we get. We get the product of the lambda i's. Right. We get the product of the lambda i's, right, if lambda is 0. Right. But remember what P is. P is the determinant of a minus lambda I. And so when you evaluate it as 0, you get the determinant of a. Right? So p of 0 is the determinant of a. So the determinant of a is the product of the eigenvalues. Okay. Second thing, you say, well, let's look at right. Let's look at V2. Right. V2, that is the coefficient of lambda squared. Right. The coefficient of lambda squared we just worked out is this thing. Right. V2 we just worked out is -1 squared summation a by I from 1 to 3, right? But if we look in here at the coefficient, of V2, right, we see what it is, right? Coefficient of lambda squared is going to be -1 cubed times summation negative lambda I equals 1. Right. So this from the above, right? If we look at our expression here, and we say what's the coefficient of lambda squared? Right? What's the coefficient of lambda squared? Oh, well, it's going to be negative lambda 1 plus negative lambda 2 plus negative lambda 3 times quantity times this constant, -1 cubed. Right? And so, right, what does that show us? That shows us that, that tells us that summation, if we sum all the eigenvalues, then we get the sum of the diagonals of the diagonal elements, in other words, the trace. Okay. And then the case for general n is identical to this. Okay. Any questions? Okay. So that's pretty cool, right? The determinant turns out to be the product of the eigenvalues, including multiplicity, including repeated eigenvalues. You can't just if they're repeated, you have to throw them in twice or 3 times or however many times. And the trace, the sum of the diagonals of the diagonal elements of your matrix, is the same thing as the sum of the elements, some of your eigenvalues. So it's basically saying that the determinant and trace of your matrix are the same as if it were the case that your matrix were a diagonal matrix of eigenvalues, right? It has the same determinant and trace of this matrix. Okay. So you might start to think, is there something that says that our matrix is just going to somehow be reduced to this? Can any matrix? What's the connection between a matrix and a matrix consisting of the eigen, the roots of the characteristic polynomial? And there is a connection. There is a connection, but I don't know if we'll be able to see it. Depending on it, I guess maybe we could do that in our last classes if there's enough time. Yeah. Roughly speaking, every matrix can be changed into something that's almost diagonal with the roots of the polynomial, characteristic polynomial down the diagonal. It's something called the Jordan canonical form. Okay. Okay. Actually, let me have you do some thinking. Let's see. Here we go. Oops. It's a theorem / exercise. It's a theorem in your book, but I think you can figure it out. So, if you have two matrices, and let's say that B and A are similar. Then they both have the same characteristic polynomial. This question has nothing to do with what we just showed, so you don't have to. I mean, it's sort of connected, but it's not. It doesn't rely on what we just showed. I'm going to put up the second question. If B is S inverse AS, right? So you have similar matrices again, and X is an eigenvector for B with respect to this eigenvalue. Show then that Sx is an eigenvector for A with respect to the same eigenvalue. That one is maybe pretty straightforward, too straightforward. turn to somebody nearby and talk with them.
They have the same.
Yeah, I think if they're similar,
Determinant. If it's similar, then I think they're the same.
Oh, so if the determinants are equal, then the determinants equal that.
Okay, would anybody like to say anything about it? About anything?
yeah, they have the same determinant, right?
Certainly, right? You know that, right? If B is S inverse A S, then you take the determinant of B, that's the determinant of S inverse AS, right? So, and then you can, right, the determinant of a product is the product of the determinants, right? And then these things are reciprocal to each other and things like that. So yeah, that's certainly true, and that's pretty closely related, right? So, right, why do they have the same characteristic polynomial? Then, right? You want to show that the determinant of this is the same thing as the determinant of this. Right? You want to show that these two things are equal. You did the homework already. Okay, great. Why am I doing this?
For like a couple weeks.
A couple of weeks ago.
Like, didn't we?
Possibly, because it's not, you know, all you need is the notion of similarity.
Yeah, I'm not that
Does anyone remember, or can you see how it goes? Right, you know that B is S inverse AS, right? So let's just do some messing around here, right? So S inverse AS minus, right? So that's one change. Is that equal to that? Why?
You multiply both sides by S.
Both sides of.
No, of this.
Yeah, but
You have to
that's.
like use associativity and like distribution to like show that those are equal.
Yeah. So here's the trick, right? You say, well, look, I would really like these things to be similar to each other. I would like this and this to be similar to each other because I know that the determinants of similar things are equal, right? We just showed if things are similar, then they have the same determinants. So can you realize this and this as similar things? Sure. You can actually just it's just a trick. You say you rewrite your I as S inverse IS, right? S inverse AS, right? And then you factor out like that, right? And then you see, oh look, you know, this thing here actually is similar to that. Right? And so that's it. Right. So to write it more cleanly, right, you say, well, say that B equals S inverse AS, then the determinant of B minus lambda I equals the determinant of S inverse AS minus lambda I, which equals the determinant of S inverse AS minus lambda S inverse IS, which is the determinant of S inverse A minus lambda I is the determinant of S inverse times the determinant of S times the determinant of A minus lambda I. So the characteristic polynomials are the same. Okay, what about the second one? The second one is just a calculation, right? You want to show that Sx is an eigenvector of A, right? We want to show that Asx equals lambda Sx, right? But why is that true? It's obvious, right? Because we know that, right? What do you know? You know that we're given that Vx equals lambda x, right? Where V is S inverse AS, right? So the end. This thing down here is equivalent to saying S inverse AS x equals lambda x, right? Which is equivalent to saying that Bx equals lambda x, which we know. The thing we're trying to show is equivalent to this, which is equivalent to this, which is equivalent to this, which we're given. Okay, so nothing amazing. Okay. Okay. Any questions? Okay, let's go on. Then, we are going to go to section 6.3. 6.2 is doing stuff with differential equations. I'm going to skip it. You can do that in some differential equations class, using linear algebra to simplify differential equations. Actually, things get much better once you have diagonalization. So, 6.3, diagonalization, or I should say they get much better once you have the Jordan canonical form. You can simplify your system of equations to something very simple. Okay, diagonalization. So the idea here is that you're hoping that what you're hoping is that if you have some matrix and you have this other matrix, a diagonal matrix of eigenvalues. Okay. You have this other matrix, diagonal matrix of eigenvalues. What you're really hoping for is that you can take your matrix and then it turns out to be similar to this diagonal matrix. That's secretly what you're hoping for, and sometimes it happens. So we'll see certain cases in which it does happen. Okay, so you have a n by n matrix, and suppose it has k distinct eigenvalues. Okay, with eigenvectors v1 through vk. Okay, so k, is some number less than or equal to n. Then the claim is that the eigenvectors must be linearly dependent. Independent. Okay. So, for example, as a consequence of this, right, if the characteristic polynomial has all distinct roots, right? If your characteristic polynomial has no repeated roots, right, then if you take the eigenvectors corresponding to those distinct roots, then you would have n independent eigenvectors. In other words, you would have an eigenvector basis. You would have a basis of eigenvectors. There exists a basis of Rn of eigenvectors of A. And we'll see that that is something actually pretty desirable. Okay. Okay. So you remember back when we did that Markov chain example, right, with the city and the the suburbs, it turned out to be pretty desirable to have a basis of eigenvectors. Right? So this statement here, this theorem here, gives us a condition under which we do have a basis of eigenvectors if we have n distinct eigenvalues. Okay, so so the proof is by contradiction. So suppose that the dimension of the span of the VI is some number that is smaller than k. Suppose that the guys aren't independent, that there's some dependence, and so their span is less than, the dimension of the span is less than k. Reorder the vectors so that the first r of them, v1 through vr, are linearly independent. And if you throw in the next guy, they are linearly dependent. Okay, so just reorder them so that the first, right, you know that the dimension of the span is r. Well, take the guys that, take the r guys who are independent and take them as your first guys. Okay. And we'll get our contradiction will be that we'll see that that we can we'll see that these guys end up to be dependent and independent at the same time. Okay. So I don't really like this proof, but anyway, it works. These guys, I think it'd be nice to do a proof that's not by contradiction for this. But anyway, so suppose these guys are linearly dependent. So I'm sorry, reorder them so that these guys are independent and these guys are dependent. Since those guys are dependent, we know that there exist coefficients, right, Ci, so that C1 V1 plus C2 V2 plus CR VR plus plus CR plus 1 VR plus 1 equals 0, right? So non-trivial, not all 0. Not all 0 such that that happens. Okay. Now, hit that with A. Okay. Apply A. Right. And we get, right, each of these guys is an eigenvector, so we get, when we multiply it by A, we get the eigenvalues, right? The eigenvalues will show up. C2 lambda 2 V2 plus CR lambda R VR plus CR plus 1 lambda R plus 1 VR plus 1. Okay. Multiply the top guy. So it's called equation 1. Multiply 1 by lambda R plus 1 and subtract. Right. So we get C1 lambda R plus 1 minus lambda 1 V1 plus C2 lambda R plus 1 minus lambda 2 V2 plus CR lambda R plus 1 minus lambda R VR plus 0 equals 0. Okay, so basically we kill off, we kill off the last, we multiply the top by lambda R plus 1 and subtract, and then the last terms vanish. Right, the last terms cancel. Okay. So you see what happens, right? The lambda I are not equal to each other. Remember that lambda I are distinct, right? So these things are all non-zero, right? All these guys are non-zero, and that tells you that, and the Ci are not all 0 too, right? These guys are all non-zero, and the Ci's are not all 0, right? Okay, not all 0, and so we have a linear combination where the coefficients are not all 0, yielding the 0 vector, right? In other words, the Vi, V1 through Vr are linearly dependent. Right? So that's a contradiction, because we said they were dependent. They were independent. Okay. So that gives us this important corollary. Once you have that theorem, then you have this important corollary that if A, right? Let me write it like this: if A has n, A is an n by n matrix, and it has n distinct eigenvalues, then there's a basis of eigenvectors. There's a basis of Rn consisting entirely of eigenvectors of A. Okay, and that will turn out to be something pretty good.